Good morning, dear listeners. In the previous session, I have discussed about various contrast enhancement techniques and also about the histogram of pixels which help the analyst to understand the characteristics of image. The contrast enhancement techniques are applied only when single data set is taken into consideration to improve the visual appearance of the image. As mentioned earlier, in the previous chapter also, that there is no single enhancement procedure that could be considered optimum or best one. The analyst may get the final image after applying number of enhancement procedures. In this session, I will be talking on those enhancement procedures where more than one data set is used to produce new data set. In this unit, I will discuss about the filtering techniques, which selectively enhances or suppresses particular wavelengths within an image and their role in image enhancement. Spatial filtering techniques are an important part of image processing systems, in particular when it comes to image enhancement and restoration techniques. The main objective of the chapter is to make the students understand filtering process in the spatial domain by convolution filtering. The various topics that we'll discuss about in this unit are spatial filtering, that is convolution, filter types, low-pass filters, high-pass filters, high-pass filters and edge enhancement filters, and some directional filters. Space-borne imagery consists of some inherent noise or interferences due to several factors like sensor error, malfunctioning of the detectors, channel transmissions, and sampling errors. The noise caused by above-mentioned factors appear as discrete isolated pixels, which are not spatially correlated with their surrounding pixels, meaning that the pixels having error appears different from their surrounding neighborhood pixels. And also sometimes the edges or boundaries between the features are not clear and discernible, which makes image interpretation a difficult task. To overcome such problem, spatial frequency or digital local enhancement technique can be very useful. So, let us begin with the understanding of spatial frequency. What spatial frequency is? So in this session, I would focus on some of those spatial enhancement techniques by virtue of which the noise present in the image can be removed and also help the analyst to identify the edges between the class objects. Therefore, let us begin with the spatial filtering topic, which allows the analyst to undergo these tasks. The term spatial domain refers to the aggregate of pixels composing an image. Spatial domain methods are procedures that operate directly on these pixels. Spatial frequency is a characteristic of remotely sensed images defined by the number of changes in brightness value per unit distance for any particular part of an image. If the changes in the brightness value are very little over a given area in an image, this is referred to as a low frequency area. Contrary to this, if the change in brightness value are abrupt or rapid over a short distance, this is an area of high frequency in the image. So, spatial frequency is expressed by the number of cycles of altering dark and light bars per degree of visual angle. Spatial frequency refers to the roughness of the tonal variation occurring in an image. Image areas of high spatial frequency are tonally rough. For example, a crossroad or field borders, while areas of low spatial frequency are smooth. For example, large agricultural fields or water bodies, as shown in the image. Now the question arises, what is spatial frequency? So first let us understand spatial frequency and its change in an image with the help of a graphical illustration. As mentioned in the previous slide, spatial frequency is a characteristic of remotely sensed data defined by the number of changes in brightness value per unit distance for any part of an image, and the same can be visualized by the graphic given in the particular slide. The image shown in this particular slide clearly shows that at a certain interval a group of pixels are having black tone, whereas other group of pixels are having white tone. But this variation is recorded over a very small number of pixels. And thereby, what we can observe is this gives an appearance of a chessboard or a checkerboard, and the image appears to be much more noisy. Not only noisy and also rough in texture because of frequent changes in the tone of the image, and thereby, conversely, the image area of low frequency are tonally smooth. And it signifies that the digital number in the image changes gradually over a large number of pixels, as we saw in the previous slide, that is water body. The possible range of the pixel values depend on the color depth of the image. Here in this case it is 8-bit image, so we are getting 256 tones or grayscales in the image. The graphic shown in this particular slide gives us a clear picture of the low spatial frequency image, wherein we can clearly observe that the tone of the image changes from black to white as we move from bottom to top. The last or the bottommost row of elements are depicted in black color, as can be seen in the image. And then next, there is a little increase in the brightness value with the color of the subsequent row changing from black to gray, which is continuous till we reach the top of the image. As a matter of fact, it shows a gradual change that gives a very smooth appearance of the element or objects which are present in the image. Thank you.